Hello everyone. This is another demo for it's evolving the landscape of the ORAN xApps that as we know that play a vital role in enabling the intelligent real-time controls and also optimization of radio access networks. And this xApp is designed as a closed loop control module to operating within the, let's say, any real-time rig, and it continuously monitor the network by collecting KPIs through REST API interface with radio units in these emulators, and then other network elements. And these KPIs include, let's say, throughput per user equipment, per slice, radio signal quality metrics such as RSR, SINR, let's say, and also the PRB usage utilizations, packet and packet loss, massive MIMO utilizations, handover metrics like triggering thresholds for A1 to A6 events. Let's take a look at the first stage in scenario generations and configuration or setup. As we can see, the number of the site and cells and the neighbors that we have here in these simulations, and we are using a new radio NR 3600 with different cells, the frequency bands, as we can, as I mentioned here, in 5G near radio, it be about here we are going to change it to let's say 100 megahertz bandwidth, and we have already defined the threshold value for the events and relevant to the handovers, and this is a RU models, advanced RF model that we are going to use massive MIMO airborne type of the antennas, 60 40 64R 8 by 8, 8 radiator rows and 8 radiators columns, and the other setup for the antenna mask. And this is we are going to use TDD mode, and let's say jumping to the user, let's say number of the user and different type of the user equipment that we have the user equipments, and can add a different type, or let's say do the 50 for the cells, and adding, let's say 10. It's a bit too much. Let's say it's 20. And we can add different slices here. As we can see, we define uh, let's say different values for different slices that we have, and already also we had defined other type of the slices as well. So now we are going to have the other customized, let's say, uh, slices here, and for example, this mission critical video user plane, and this we are going to change this value, for example this one, into 150 myot 01, and also now we are going to find, okay, this is anomaly injections. We are going to create an anomaly for both radio degradation and the throughput degradations here. And this is the features of each anomaly that's given to let's say affected area, also Here would be these are the defining the areas that's already we have defined for simulations, emulation in the map and affected cells. Uh, Here would be considered it's all cells and uh, also let's say potential PCI, this is neighbors. Okay, this is a connectivity anomalies. Also, we can add some different anomalies. Let's say RRC connection reject, anomaly of PDU session failure, and another anomaly. Let's say service-related call drops, and the value of the default is the is has been set here. And then we are going to enabling, yeah, these are the model preview is still, yeah. Now we are going to use, let's bring the or xApps here that has been designed, yeah, so save it, sorry. And now we are going to use or xApps to simulate it and what's going on by constantly analyzing these metrics. xApps can detect anomalies such as the throughput degradation, radio signal deterioration, and the load, let's say, balance across the network cell. This deteriorations could be yes detected through different machine learning approaches here. To enable this, it utilizes an unsupervised machine learning method here, and also supervised both, and it could be explained in detail in the next demos. And also, let's say the model could learn, let's say, the typical network behavior and flag the deviations that suggest underlying issues like interference and suboptimal beamforming, massive MIMO order, congestion, and so on and so forth. And upon the detecting an anomaly, the xApps evaluate the context and applies machine learning driven policies to correct this action. These actions are executed through RESTful API commands sent to the relevant, let's say, these emulators that we have via a TeraVM via the rig tester, and available corrective measure includes, let's say, adjustment transmission power for the cell, modifying massive MIMO order, switching between a different, let's say, for example, 8T between 64T, 64R, 16T, 16R, and so on and so forth, and changing the threshold of, let's say, A1 to A6 events, handover events, and dynamically allocating the bandwidths among the different slices to prioritize the high demand and critical services. This accepts make process informed by the policies is informed by the policies that derive from historical data and optimization target that has been achieved through the offline mode of this uh, via rig tester. When it's going to be, let's say, true, data could be generated too fast, and the data can be stored as a CSV file, and these are going to be used for the aim of the data training, and also now we are going by detecting these anomalies and applying the real-time control. It enhances the network performance as it could be seen. Thank you for this part. Now the setting of our scenarios is ready, and let's say with we have the different cells. These are the interfaces that as E2 interface we are going to connect to we test through our xApps that is written in Python. And yeah, this is something that will be done in our demo that will be shown in the next let's say demo. Thank you for your attention.